Hello, I'm Isaac Ajao. Today I want to talk about hypothesis testing, and I will use t-test and Anova as example using Python. Let's go to Python and see t-test and Anova. Then how do we design our hypothesis? Now, first of all, we have to formulate the null and alternative hypothesis. What do you want to do? For example, the last video, I made mention of population and sample, and I explain how sample is drawn from population, and such population must be the one that is all encompassing. Before we can simulate such a data, we must have specified the range, which I explained in the previous video. But today we want to set hypothesis. Now I want to make use of the population mean generated and the sample mean. You know, we have declared that the mean should be 50, and the sample mean must be very close to population mean. And we have tested this. See, the population mean is 50, the sample mean is also 50, and we tested this, and that's how we have population mean to be 50 and sample mean to be this. Now look at it the way I set the hypothesis. Not the hypothesis each not. The meaning is that the mean of the sample is equal to the population mean. We assume it's an assumption. Hypothesis in statistics means assumption. So when we say, I can as well say mean in bracket population or x bar population equals mean that of sample. That's what this means. So an alternative hypothesis say the mean of sample is not equal to, so we just say they are not equal. Now we must set decision rule. Decision rule should be decision rule. Decision rule, we comment it. Decision rule is reject each not. Reject each not if p-value is less than, just use this, less than the alpha, that is alpha is level of significance. So in most cases we use the default 0.05, the probability of committing type 1 error. Now obviously you can see now population mean is equal to 50, example mean is this. So we are saying that this and this are equals. One of the attributes of a good sampling method. Once you want to take example and the mean is not equal to or very close to that of population, the sample you are taking from that particular population, if used for analysis, may be biased and may not be reliable. Now, having done that, now type 1 error is rejecting the null hypothesis when it is true. And that is what we call level of significance. I've defined it here. We have two types of error. Type 1 is rejecting the null hypothesis when it is true. It's a serious offense when you are rejecting hypotheses that are supposed to be accepted. Type 2 error is failing to reject the null hypothesis when it is true. For failure to reject it is also an offense. We call it type 2 error, and these are the probability assigned to them. Now, this is it. Type 1 error rate is 0.05. Now, this is what we call level of significance. And some researchers call it cutoff mark. So once in statistical inference, before you take a decision, if the p-value you get is greater than this, you do not reject each not. That means it is not significant. The difference is not significant. It depends on what you are working on. If it is relationship is not significant at 5% level of significance or 0.05. Now I want to conduct t-test. We are talking about This is all these I'm talking about. They are all under hypothesis testing and statistical inference as a whole. We want to conduct t-test now, picking one sample, independent samples and paired. These are the common ones. Now, having installed our libraries in Python for skippy test, t-test, one sample. See, t-test, this IND is independent. So, I want to now bring them together using the first one here. See, for one sample, this is t-test p-value. So t-test one sample from population mean we have already declared. We have a sample here. These are sample we have generated. The previous we have sample that we have generated. Generated our sample. I explained this in the earlier video. This is the sample we have generated from population. So we'll be making use of this down here. So this is sample population. We want to now see. We want to test. What we want to carry out is that we want to see whether the sample and population mean are the same. So it's going to give us the p-value also. And this is the code, this command for it. Once you type this function, Python is sensitive to this. All of these ones, they are just decoration. What is important here is the t-test underscore one sample. Let me build it. You can see one sample t-test. This is test statistics. If you do it, even using our calculation, doing it manually, you're going to get this. You can approximate this to 0.48. That's minus. So here, p-value is 0.6305. This is greater than level of significance. Here, we are going to reject. We do not reject null hypothesis. When we do not reject this, we are saying that the value of the sample mean and the value of population mean are equal. We do not reject each not. What does each not say? It say there's no difference in the mean of sample and population. You can see. I think I wrote it somewhere. See, the mean population and the mean of a sample, they are equal. This is each not. So we are accepting this. So we do not reject it because this scientific way of proving that. So it's an inference. So there's no difference. There's no difference in the mean of population and that of sample. That is noted. Now for independent sample now, this is the main thing we are going to do. T-test, this is the code we are using for it as far as Python is concerned. So for independent t-test, we need two variables. The question here is that you have two population or two samples and you want to answer the question that says, are their means equal or are they related? So now here we need to get our p-value, we need to get this t-statistics. And we're going to, if we are using table of the t-test from table, this is where you're going to get the value. But computer will generate p-value and we know the division rule. So we are now generating another sample to make it 2. We want to test whether they are related or not. Sample of 100. Now from population, we are generating from the population we are generated earlier on. Now I've explained this before. Now these are the two, sample 1, this sample 2. We want to see whether they are equal or not. And that's why we are using t-test. Let me build it. You can see independent sample t-test. The value here is 0.2619. You can see. And the p-value is 0.79. It's also very high. Now we do not reject each not here because it is greater than 0.05. Meaning that they are equal. You can see the mean of sample, first sample and second sample are equal. There's no difference in it. Going to the third one, which is paired. Paired is just like one population divided into 2 or one sample divided into 2. Independent means they are not related. One class, another class. One group, another group. So now we use sample before, sample after. For example, now a population, maybe some people they visited the hospital and they are giving one pain reliever. And they now test their temperature before they visited the hospital for admission of drug. The temperature before, temperature after. See, things like this. So this can be applied in so many, it can be also applied in engineering, it can be applied in environmental, it can be applied in science, everywhere. So what happened before and what happened after? You pick example, you divide into two. Population divided into two. You want to see what happened before and after. So in this case, it's paired. It's the direct opposite of independent. Now, sample before we generate value. If you have an sample after is this. I'm just generating this because I don't have data on ground. But if I have data, this is the method you're going to use. So the t-test, this is the one talking data similar, paired. So sample before, sample after. The key code we are using here is t-test. Let's check it. See, this one is independent. This is paired. It's paired. So now you can see it before and after generated here. If you have your own value, you can just put it here or your data. So let me enter this. This is highly significant. Just go straight to the p-value 0.0015. Very high. This one is lower than 0.05. In this case, we have to reject each node, saying that the mean of the first sample is not equal to the mean of second one. That is just the meaning of this one. And in this case, the difference between the temperature before and temperature after, for instance, they are not equal. The means are not equal. So it means the difference is significant, not just as random or chance. It's not by chance, it's significant. So let's go to one way and two way Anova. Anova means analysis of variance. We use Anova generally for comparison of means when the number of groups we are considering are more than number of groups is more than 2. When it is 2, we use t-test. That one sample or independent or paired. But when it is more than 2 groups, 3 groups, and so on, we use one way or two way. We also have factorial experiment. We have so many of them like that. Considering one way now. So I have these two groups. These two groups, we have score. Two variables. We have score. We have state. Now the idea here is I wanted to, when you are in a class, you have students. In this case, I generated 90 students, mean of 50. These are their scores. I assume it's over 70, and the mean score is 50. This is standard deviation, 90 students, and they are from Ekiti State, Osun State, Ondo State. So I want to see whether the mean of their scores vary across the 3 states. So whether there is going to be difference in the means of their score. Maybe the state where they come from has something to do with the score they have. I'm considering only one factor, and the factor is just state where they come from. State in Nigeria. These are 3 states from Nigeria, southwest in Nigeria. So now I want to test this. What I do is just the NP random is I've explained this to generate a normal distribution. The NP is from a NumPy library. The repeat here is that I don't want to be wasting my time by repeating Ekiti Otun in 90 places. So what I need to do is just to write the 3 level or 3 categories. Ekiti Osun Ondo, and I put that here. Python will now repeat each of these 30 times. It will repeat Ekiti 30 times, Osun State 30 times, Ondo State 30 times. So we are going to have this as 90. If I put tile here, there's a way if I put tile instead of repeat, it will repeat this once, and that's it once, like that up to 30. So let me print this and see. So now the first 5, Python will give you when you have a long data like this, it will give you the first 5. Now see what it has generated. These are their scores. And these are their state they came from. Can see repeat. If I change this one to tile, can see it has changed the Ekiti Osun Ondo like that. But I prefer, because it's just one factor, repeat. So this is it. So this is data. Now I want to perform one way. This is one way. one-way Anova. I want to perform one-way Anova. Can see this. OLS means ordinary least square. Now the score, this is dependent variable. Score depend on the state they come from. Can see the question. The second question is that I want to see whether the state depend on the state the student come from. Now, the state has how many level? 3. Ekiti, Osun, Ondo. Now, the data is DF. So the fit here is that we want to see the model fit. So the ANOVA table is, this is the function, which we have already declared here as SM. So you can see the ANOVA linear model. So we normally do ANOVA in regression, and we do regression in ANOVA. So that's why we are bringing it together. They are all under statistical inference. Now, the one way, all of this one, they are just to show us the table. So you can see the result. This is the result, the date, the time. What is important here is the R square. I just say R square, the F, the AIC, BIC. These are method criteria. These are criteria information and information criteria. And we have a degree of freedom. The number of observation is 90. Degree of freedom is 87. You can see now the non-robust, the covariance type, all of them here. This is another table we are talking about. Is summarized one. And you can see each of the level one is taken because of the degree of freedom. Ondo, Osun. So it will be taken as reference group. So you can see here, summary here, the p-value, none of them is this for intercept. None of them here is lower than 0.05. So whether you come from Ondo or from Osun, it doesn't affect the score you are going to get in that class. That's what it means. In this case, we are not going to reject each note, saying that the means are equal across the 3 groups. And these are many results. Let's go to two-way Anova now. I don't need to talk much here because it's just the same way. The only thing is that I've introduced another factor. I introduced another factor and I use style for this. Let me quickly explain this. The state from which the student came from might affect their score. And I introduced another one called secondary. The secondary school they attended. Is it public or private? So you can see I put 45 here. The reason why I put 30 here is because I multiply this by 30 will give us 90. Because that must be equal to 90. So public and private. You see, this one will be repeated, but it will be in tile form. Public, private, then public, private, public, like that. Times 45 give us 90. So let me build it for you to see. Now see now, state. Next one there will be, this one private, public, private, public, private. So we want to see whether the second factor we have influence on that. So we want to perform the two-way Anova now. The same, the only difference that is that I want to see the interaction here. I want them to be, to all of this to come out my results. So if you compare the code here with the code here, there's no more difference. The difference is that this one we have 1 here, and here we are having 2. Anytime you are having more than 1, you can have interaction. This interaction. This is where we do it in R. This is where we do it in MATLAB and all other software. So let me build it. So the result is more complex because we have 2 independent variables, 2 factors. That's why it's called two-way. One way is 1 factor, 2 ways 2 factors. We can have 3 factors. We can have factorial when we have many factors. So you can see the interaction. So Ondo, the p-value here, though none of the coefficients is 0, it means they all contribute to their scores. But significantly, they are not. None of them is significant. Ondo is not significant. Osun is not significant. See, okay, combining state with the public or in the kind of school they attended, none of them is significant. So overall, I can say that whether you come from Ekiti or Osun, anywhere, any state you come from, or the kind of secondary school you attended, it will not contribute, as far as this data is concerned, to the score you are getting in my class, because I take this as if I'm doing my class. So thank you. Thanks for listening and watching. Watch out for the next video.